Good morning, everyone, and welcome back to a new week of 3205. Last week, we were talking about special resolution and temporary resolution, if you could remember. Now, before we begin today, I want you to visit this website. It says www.planet.com. Okay, you can simply type www.planet.com, or you can click on this link and visit this website. So I have already opened this website on my browser, and you will see that this URL is for the planet imagery and the archive. So they not only store or catalog the imagery collected by the company Planet, they also catalog the imagery from other companies as well. For example, they also catalog Rapid Eye. Okay, so yes, so it's archived back to 2009. So starting from 2009, you can have data. You can have access to data of Rapid Eye. Obviously, you have to buy it because this company is a commercial one. And I think I have already shared an interesting link with you last week. Let me quickly check. No, I did not. Okay, so I will try to find it out. So the link says that how these commercial companies are, yeah, I didn't share it. How the commercial companies are doing monopoly in terms of satellite images, and how they have to do a lot of paperwork releasing any satellite data for public, even for non-commercial users, for example, research and academia. So saying that, Planet used to have this policy of giving data away freely for some data of PlanetScope for the research purposes, but now they are not giving it away anymore. They have stopped it. The reason behind it is now they have a contract with the defense sector of US. So they cannot just give any data away based on because of that contract. So yeah, so there are lots of things, many improvements that we can make for the humankind, but humankinds themselves are working as a barrier towards these improvements and developments or the research works. So have a quick look in this website. Have a quick look in their products. They're very nice. Okay, and why do I say very nice? Because if you look into the SkySat, the SkySat has 50 centimeter resolution. So 50 centimeter resolution, just like I said, you see, you can detect the waves in the sea. All right. So 50 centimeter resolution is very high resolution, special resolution, and this 50 centimeter resolution means so 30 centimeters make 1 foot, sorry. Okay, right? So 50 centimeter is a little bit of 1.5 foot. Okay, so it's very high resolution. You can detect a car. You can count the number of vehicles on the street. So the PlanetScope, the data they were giving away freely, it has a 3.7 meter spatial resolution, which is still quite good, much higher than Landsat, or almost 1/3 or 3 times higher resolution than Sentinel. Whereas Rapid Eye has 5 meters resolution. These data can, I think, can also be accessed from Sparso, because Sparso buys this data, not all of them for Bangladesh, but some of them, and then they resell this data using the value of government, value set by the government. So if we look into this, their metadata, or their information, then you will find the PlanetScope has 4 spectral resolution. So RGB and near infrared. We will talk about this today. This is our topic. And it also has visual 16-bit and analytic, visual 8-bit and analytic 16-bit. Okay, that's radiometric resolution. We will also talk about this today. So that's for PlanetScope and Rapid Eye. Okay, and Rapid Eye has one additional band that is called Red Edge, and Red Edge is quite nice if you are going to work on vegetation. So that sits between the red band and the near infrared band. So it's the edge of the red band. So SkySat has 5 bands. So red, green, blue, near infrared, and a panchromatic band. So panchromatic bands, they are usually they're higher resolution. And so what is a panchromatic band? We will talk about in this class, not today's class, but in the future classes. So next is their pixel resample, that's spatial resolution. This one has 3 meters, 5 meters, and 0.5 meters. Which is a pan-sharpened multispectral. So multispectral are these bands. Okay, these bands, these visual bands are making it multispectral. And so these multispectral bands usually have lower spatial resolution than panchromatic bands. So if a panchromatic band has 0.5 meter spatial resolution, then a multispectral band might have 1 meter spectral resolution. Yes, I'm recording. Sorry, I was just quickly checking. So what you can do at the time, since you have information of 0.5, you can resample using the panchromatic band. You can resample or sharpen the multispectral band. And when you do that, the product that you get is called pan-sharpened multispectral. You do not have to understand all these things. We will discuss them in future lectures. So that's why it's called pan-sharpened multispectral, which is 0.5 meters. So it also has radiometric resolution. For the visual is 8-bit, and for the rest is 16-bit. Okay, and in terms of the accuracy, it has less than 10 meter root mean square error, so which is good. And the file format is GeoTIFF. Anyway, so that's enough information. All the topics that we were discussing in the last class and we will be discussing today are given here for PlanetScope. Okay, then you may want to visit other website, for example, Sentinel as well, Sentinel-2. You can just type Sentinel-2. And then you will have the Sentinel-2 mission status or the information. Okay, so that's from European Space Agency, ESA. And you will have data products. Okay, so you will find out that there are how the Sentinel-2 is working, who are responsible for what. Okay, and you will find lots of information, documents, including the user guides. How are you going to use Sentinel-2 multispectral imageries, or the synthetic aperture radar, which is a radar, and so on, and also the technical guides, how they're built, how they are collecting the signals and all other things, and also how can you apply them. Okay, so as you can see, there are multiple sectors that you can apply this data very easily. One of them are land monitoring and climate change, and also emergency management. Okay, so Sentinel-2, then you might also interested to look into Landsat. So maybe Landsat 8, the latest one. The Landsat 9 will soon be up in the sky. So Landsat 8, you can go to here, or you can go to the Landsat Science different website. So have a quick look. It gives, so there are 9 bands. Remember, there are 9 bands, okay, in Landsat 8. And then we have 2 thermal bands. So if you think of the entire spectral resolution of Landsat, then it would be 11. Okay, because it has in total it has 11 bands. But if you think of what is the spectral resolution of the multispectral sensor used in Landsat 8, then there would be 9 bands. Okay, why? Because the multispectral or the OLI or the land operational land imager has only 9 bands. But then if we think of the thermal infrared sensors, we have 2 bands. Okay. So, yeah. So you can also go and see the website that was produced by NASA. The previous one was from USGS, United States Geological Survey. Okay, so that's the information about Landsat, and you can quickly go through this information from the left side. So here as well, here you will see the Landsat 8 bands. There are 11 bands in total. Okay, whereas these two, they are thermal bands. So these are the, it's more detailed, more technical, because as you can guess, NASA is more technical, so they are giving more technical information on each bands, and they have said something. So go through them, read them, and try to understand what are they trying to say. Anyway, so before I begin, I wanted to show you something. I wanted to show you the difference between two different spatial resolution. Okay, and also the radiometric resolution, although it might not be quite visible in these examples. However, we will try. So this data is from Landsat 5. Okay, so I'm going to put this one in false color image. So near infrared into the red channel. I clicked on the near infrared into that is band 4 into the red channel, and the green is band 3, which is red, and the blue is band 2, which is actually green color. So I say load RGB. So now we have one data loaded onto this place, which is Dhaka. So this is Dhaka. Okay, as you can see, this is Dhaka, and then if you move around, you will see the surroundings of the Dhaka. So how am I moving around? I'm using these here, the region of interest. Okay, so you can see the Buriganga River, and then here you go. Okay, so the Ramna parks and others are located in this region. So this is a false color image. So vegetation appears to be red, appears to be in red color, and the water bodies, they are in darkened color. So now if we look into this data, then we will find that much of the city is covered in built up areas. Okay, and there are not so much vegetation around it. And also we have some clouds in this data. So the clouds are blocking the signal. Okay, and the clouds, they are also making some shadows. If you look into this section, you will find there are shadows. These are the clouds, and these clouds are making some shadows. And computer or the software by itself doesn't understand what a shadow is. So it will think, if you process this data, it will think that these vegetation and these two vegetation are different. Okay, because the signals are different. Because this signal has shadow and this signal does not have any shadow. So it has high albedo. What's a high albedo? Albedo is the reflectance. Okay, whereas this one has lower albedo. So there's a difference or fluctuation into the signals, into the in the reflectance curve. So yeah, so that's why shadows will create problems for you. just look out for these shadows. Okay, and then when we come down to these, does it called estuary? Okay, so if we come to this big part of the river, then you will realize that the water has now transformed into blue color instead of this dark color in these regions. Okay, so the reason behind this, also for here, it's a little bit blue. It's because the water is not blue anymore. The water has lots of sediments. So it's dull now. So by dull, what I mean is in Bengali, it would be kola. Okay, so there are lots of sediments. It's not giving away its blue color. So that means it's not absorbing things like it used to. I mean, the light cannot pass through the water anymore. So the water is reflecting some of the signals. And what are they reflecting? They're reflecting these color of the sediments. All right. So if it's dark, they're reflecting dark. That means they're absorbing some of the energy and they're releasing some of the energy. I would say equally. And if it's yellow, then it's reflecting yellow, much of the yellow color. Okay, so the yellow sits between red and green, maybe. So to some extent, it's showing blue, or yeah. So you see, we used blue band. We used green band in the channel blue, so it's reflecting blue color here. So that means much of the color of the water is blue. And the same thing you will observe in the data. This data on the left side is from Planet. So the spatial resolution of this data is 3.7 meters. So, or we could say it's 3-meter spatial resolution after the resampling, after the processing of data. Whereas this one is 30 meters resolution. Now you could say that, sir, this one has, sorry, let me minimize this. So you could say that, all right, so if we look into this data, this seems very smooth, right? And if we look into this data, it does not really seem that smooth. And when we zoom in, it seems very smooth in this image. For example, if we go here, it seems very smooth in this image, but then when you're zooming in here, for example, it does not seem really that smooth. The thing is, in this region is a little bit homogeneous. That means it's a plain land. Okay, it's Dhaka, so it's plain land. There are lots of vegetation, lots of greeneries. If you go outside of the city, and then there are little canals or water bodies you can see. But then this region is from Chittagong Hill Trade. So more specifically, this is Kaptai Lake, this is Rangamati, and then you will realize that it's a hilly region. So since it's a hilly region, and when a satellite data is taking this photo, one side of the hill, for example, if you look into this part, one side of the hill is well lit, and the other side has shadows. It's underlit. Okay, so because of this condition now, this image is not smooth. Okay, it does not seem as smooth as this image. But then if you correct this this error or this bias, which is called topographic correction, we'll talk about topographic correction in the coming lectures. So if you perform topographic corrections, so topographic corrections fixes these sorts of errors arise due to the uneven topography or the rugged topography. So after fixing these errors, this image would be appearing just as smooth as this one. Even if you look into these pixels now, they would seem that, okay, they are containing much more information because they are higher spatial resolution. On the other hand, if you look into this image, then you will realize that they are containing less information because this one single individual pixel represents 30 meters, whereas this one represents 3 meters. So that's 10 times better than or higher than any pixel that this Landsat could represent. I'm talking about in one direction. So now you might say that, okay, so how can we improve this image? I mean, the look of it, all right? How can you improve? Let me go here. Let me say enhance. So we can say, all right, so tell you what, let me do from here. Sorry, no. Let me do interactive stretching. So that's the histogram of the data, right? So this is the input histogram. And if you do not know what's a histogram, Google it and see what's a histogram. So the histogram is here are the it's the signal, okay? It's the signal of the bands, okay? The bands that we are receiving. So these are the digital numbers, and these are the range that we have 0 to 255, okay? So why? Because we're seeing although this data is 16-bit, but we then resampled it down to, or scale it down to 8-bit. So that's why we're seeing 255. Remember that this one is 16-bit, right? So why do I say this one is 16-bit? Because it says it here. So analytic is 16-bit, okay? But visual is 8-bit. So the data that we have accessed is, if you look into the name, this is analytic. So analytic multispectrum, okay? Anyway, so this is the histogram. So let me change the histogram. So stress type, let me make it, sorry. Let me make it linear 2%. And now you will find that, okay, so now vegetations are well defined from these images. Now you can identify these every individual vegetations almost. Okay, so there's a group of trees maybe, and here as well. And these are the shadows are also identified very nicely. So vegetation, bare land, water bodies. Then if we go back into the hills, we will realize there are more vegetation. Okay, and if we come back to the settlements, this is the city, and you will realize these are the streets, and the streets are stretched out in this image. And here is one. This is actually the stadium. Okay, and then the streets are again, and these are the settlements. These are the settlements along the islands. Okay, so you can change the histogram again. You can make it let's say simple linear. Okay, so now the linear, it has changed. You see this graph is changing. All right, so when you are making it linear, then now all the vegetations are very well visible. Okay, and the red light has become very, what should I say, red light is the focus now. Okay, because I'm doing it in the red channel, so others are not that much focused. So yeah, small islands are also visible in this image. So in this image as well, now I'm going to enhance simply from here. So let me enhance to 2%. Now if I enhance to 2%, then you see what's happening here. It's much of the information of the vegetation is gone. Okay, and also if I now do it linear, then the information are back. Okay, back to the previous. And then you can do also square root. You can do Gaussian, and so many things. There are so many things to play around. So okay, so how to access this data? To go to Earth Explorer. So that's Earth Explorer USGS.gov. Go there. Then log in using your ID. Okay, create one ID. If you click login, then it will ask you to either log in or register. So create one ID, and so excuse me, yes. So what you can do is you can go to, for example, you're interested in Bangladesh. Let's say I'm interested in my hometown, so I'm going to click. I'm going to go to Rangamati, then say geocoder, path and row. I would say polygon. Okay. So as for the polygon, can I draw polygon? Sorry. Right. Use map. Okay. So I'm not sure how to add any polygon here. It's a little bit, they changed their website a little bit. So, okay, I'm going to do 1, 1, 2, 4, and 4, 4. Show. So 1, 3, 4, 1, 1, 3, 5, and 4, 4. Okay, so 1, 3, 6, 1, 3, 6, and 4, 4. Yep. So here you go, 1, 3, 6, and 4, 4. That's their the path and row number of Landsat. You can actually draw a polygon and then identify that I want to find out the area between this region, but I'm not quite sure how to draw in this changed website. So yes, so that's my area, and I want image from, let's say, January 1st till January or February 1st. Okay, and the data sets, I want to go to next step. So data sets, there are lots of data sets, and you can access the Sentinel-2 as well from here. But I would not suggest you to access Sentinel-2 from here. Rather, use the Sentinel's website, Sentinel Data Hub or ESA Data Hub. So we are interested in Landsat. You can also download these digital elevation data, the SRTM, 1 arc-second global. Okay, so 1 arc-second global is arc-second. So it's an arc and then second. So it's a 30 meter spatial resolution. Okay, so I'm going to select Landsat, and in Landsat there are 2 subclasses: Landsat Collection 1 and then Landsat Legacy. Okay, but we're not interested into Landsat Legacy, and we are interested in Landsat Collection 1 Level 1 or Level 3. So Level 3 is the process data. Okay, so you have dynamic surface water extent, then snow-covered area, burned area. We don't want that. Landsat 2 is the atmospherically corrected data. So the noises that were created by radiometric error and the atmospheric error or the influence, they are corrected in this level. However, I do not want that as well, because I want to do all these things by myself. But you can download data from here, the Landsat 8, 7, or 4, 5, anything, and have a quick look. How do they look like? Because they removed the effect of different particles in the atmosphere. So I want the data, the raw data. So I would select Landsat Collection 1 Level 1. So in this case, Landsat 8, because there is no 7, 4, 5 in 2020. So additional criteria. In my additional criteria, I'm going to select, whoa, they changed a lot. Right. So I'm going to select the land cloud cover. Okay, I'm going to select less than 10, and the scene cloud cover as well less than 10. Okay, so yes, and then results. So you can click results, sorry, you can click results from bottom, or you can click results from up here. So it's going to search. Since my date is quite only a month, so the result is very fast. And I have 4 data within this month. Okay, so one is collected on 28th January, 28th January, and then 26th January and 26th January. Okay, why there is only 2 dates different? Anyway, let's see. So I can see the footprint here. I can see a sample, okay, of the image. So I'm going to load the image. Oh, okay. So it's on the different part. So that's 44, 45, 43, 137. Okay, and then okay. So there is no image that time in this location, I think. Yep. So I do not have any image in my area. So could be because it was covered by the cloud, because I said I want less than 10% cloud. So what I can do is I can go back to the additional criteria and say, all right, I want a little bit more. Let's say 30%. I don't mind clouds. So let's say 30% and go back to results. And it will show me, I was looking for 136, 44. Now it's showing me 136, 43 and 44. So 43 and 44. Now if I load, yes, my footprint matches. I load the data. Okay. So search criteria. Let me close this. All these pixels. Yeah. Oh, okay. So it's gone. Huh. So it seems less user friendly. 136 and 44. Okay. So anyway, so that's 136 and 44. Where is it? 44, 135, 136 and 44. So that's my image. Okay, this is my image. So it has some clouds. It has clouds in this region, but here is the Kaptai Lake. I can see my image. All right, so I can look into the metadata. Just a quick load of metadata. So this is my image, and this is the thermal band. So in the thermal, you will find the vegetation has almost the same reflectance, whereas water bodies has a little bit of less reflectance. So they are cooler than the land. Okay, and there when there is a high density of vegetation, it has also less reflectance. So this part is a little bit darker. But this image is not, because this is just a sample image, and this is the cloud information. Okay, and since this is just a quick look, so it does not really contain what the satellite image really looks like. So it's just a sort of thumbnail. Okay, so and if you look into this data, you can look into the different metadata there. When the data was taken, their nadir of nadir, the data was taken at nadir point, and the angle of the sun. So many information. Okay. So close. If you want to download, if you are logged in, then you can download directly from here. Okay, or you can order it here. So if you order the scene, I mean, if you want to, if you do not want to download immediately, or because in this download scene, tell you what, show you, because there are some options. I hope I remember my information. Okay. So for example, I want to download this image, right? So I click on these, and there are lots of options. So do you want a single color image? You can download it. It's just 7 megabytes. If you want to download the thermal image, it's just 1.5 megabytes. And the quality image is even less. If you want to find out only the geographic reference, then that's that. But I want to download this one, level 1 geotiff data product, which is 851 megabytes. So you download this, and if you click download, that it will be going to your order scene. I'm not going to order it. Close. Then you will go to this order scene option, the cart, and then you will check out. Okay. So they will email you once the data is ready to download, and you come back and you download the image. That's it. So that's how you can download data from Earth Explorer. Okay. Excuse me. .usgs.gov. You could download the data from the repository or the database of NASA. Okay, you can download this data from ESA as well. Okay, European Space Agency, and there are some other websites as well. So just use this data, download 1 or 2 data if you have unlimited internet access, and have a look. How do they look like? Also, I think I have already given you the how you can download and install the software. Meanwhile, you can also download Beam. You can download, is it the same company? Oh, right, yeah. So you can download Beam, okay. You can download this Beam, which is a very basic tool for remote sensing. It works in the same way. Yes, it's the same thing. So software, I have Beam, no. So you can download and install it. It works just like NV. You can open the data and click on different things and see how it goes. Okay, experiment it. All right, just like monkey business. So monkeys, they do experiments, and doing that, they start learning. So these are the also, this one is 16-bit, remember, and this one is 8-bit. So I'm going to close everything because now we'll be having a very short lecture. Okay. So we talked about temporal resolution and spatial resolution in our last class. Today, we're going to talk about the rest 2 of the resolutions. And these 2 are spectral resolution and radiometric resolution. So spectral resolution, as you have already understood, I think, is the number of bands that it has. The visible range, a black and white film, it captures data from 0.4. I mean, black and white films mean you can turn on your black and white filter on your mobile phone and take a photo of you in grayscale, that is black and white. Even if you are taking the photo in black and white, it actually taking in all this information and converting all these 3 red, green, blue information into one single channel. That's black and white. Okay. On the other hand, if you make a color film, then this color film is actually taking the signals and blending these signals and making the image or the photograph colorful. Okay. And the 3 signals that it takes is the blue, green, and red, and they are separated using, I mean, these channels. This is, I'm not saying that these are the specific color, but I'm saying the channel of these colors or the channel of these spectrums. So the blue is ranging from 0.4 to 0.5 micron. So micron is the micrometer. If you divide 1 meter in 1,000 times, that's the micrometer. Okay. And you can also say it's 400 nanometer. All right. So 0.4 micron to 0.5 micron is the blue channel, 0.5 to 0.6. So that means they have 0.1 micron differences between each channel. So that means the length of each channel is 0.1 micron. Okay, whereas do you remember the characteristics of hyperspectral is their length or the width of this band are 0.02 micron, so much less than or very small, finely separated each band into the hyperspectral bands. So 0.5 to 0.6 is the green, 0.6 to 0.7 is the red. So our visual range, the human eye can detect, is the wavelengths, which are 0.4 micrometer to 0.7 micrometer. That's all we can see. Okay, so this is called spectral resolution, and these, instead of saying them as the channel of different spectrums, we simply call them bands. Okay, so one satellite image, how many bands were collected, or sorry, how many bands were used to collect that one satellite image is the spectral resolution of that image. So for Landsat 8, it uses 9 spectral bands or 9 bands for detecting its multispectral image. That is the image that you see. Okay, so it starts less than 0.4 that contains the information of the aerosol. Aerosol is very important for us to study, and that's why Landsat 8 started collecting data on aerosol, whereas Landsat 4, 5, and 7 does not collect any information on aerosol. Okay, so now I have a very quick question. Why do you think aerosol is very important for us? Or why do you think aerosol is important for us to study? Okay, some of you might be thinking, okay, so aerosol is the chemical that kills insects. It's not aerosol spray. Talking about the atmospheric aerosol. Okay. So it's they are sort of small material, foggy material. They create kind of foggy environment. Where can I find? So you see, that's nice. It says marine aerosols. So marine aerosols, yeah, that's one example. Can anyone tell me, any guess, any idea why the aerosol is important for us to study? I mean, scientists must have failed to realize the importance of aerosol in the 1980s or 70s or 90s, at the beginning of 90s. Otherwise, we would have sensor in, yeah, now this one is important. So now we would have the sensor detecting aerosol in Landsat 4 and 5, because Landsat 4 went up in 88, I think. Okay, so there are the aerosols have very significant impact on our life. Okay, and it has very significant impact on climate change. And that's why one of the reasons that Landsat 8 can detect aerosol or is detecting aerosol. So the significance is that okay, so the significance is that in climate change, we're saying that the world is warming up, or the Earth is warming up, right? The atmosphere is warming up. But then the scientists also realize that it's not warming up as it's predicted to be. Okay, especially in the industrialized regions. So when the industrial revolution happened 200 years ago, the atmosphere around it increased, the temperature increased significantly. After some time, the temperature started stabilizing, getting stable. Okay, it's not increasing as it should be. So what was the reason behind it? One of the reason was the aerosol. So what aerosol does is it sort of works as a barrier. So if you have a foggy morning, you will realize that the sunlight is not coming, so there is not much temperature, right? I mean, you will not feel warm, you will feel cold, you will feel colder even, okay? But then suddenly the fogs, they go away, and then you realize that the sunlight coming in, and within half an hour, it's quite warm in a wintry morning, okay? So just like that. So these industries or these factories, they were also releasing aerosol. So these aerosol, they were actually blocking out the sunlight. They were working something like cloud. And since they were blocking out sunlight, but they are not really clouds. So because you cannot really see them in naked eye, using naked eye. So what happening was they were blocking the sunlight. Since they were blocking the energy of the sun, now the industrialized areas, they were getting less heat from the solar energy that they should be, and that's why it wasn't really warming up, okay, like it should be. So that's one of the importance of the aerosol that we should study in climate change and global warming. So anyway, so the aerosols and all other bands, they are located in this region for Landsat 8, and near infrared, middle infrared, all other bands are located in this on the right side. So they have higher wavelengths, lower wavelengths. So one quick example of these bands, you will realize the band 1, band 2, band 3, band 4, if you load them individually, then their colors are changing. Why? Because the information that they have received in that certain spectral channel has changed. If, for example, if this is a river, if something is river, a river is located here, then river is in blue. So in this image, that would be that would reflect some of the energy that might have some high albedo, okay, or higher than other, something like that. On the other hand, if we go to the higher significant, let's say higher band, for example, band 7 of Landsat 4, 5, okay, or 7, then we will realize that water does not have any reflectance in this band. So now it's very dark, okay, whereas the built up areas, they have reflectance, still reflectance, and since that's why they are very bright. Okay. So spectral resolution, Landsat 7 and another satellite Aster. So one quick note here, every satellite is designed to receive the signals in specific bands. So if you talk about one satellite, then it has fixed resolution for all these 4 resolutions. It has fixed spectral resolution. It can detect the fixed number of spectral channels. Landsat 7 has 1, 2, 3, 4, 5, 6, 7, and one thermal band, 8 bands. Okay, whereas Landsat 8 can detect 11 bands. So 11, it has the 11 for the spectral resolution. They have fixed spatial resolution. Okay, the 30 meters is their fixed spatial resolution. They have fixed temporal resolution. Sometimes it varies. It could vary a little bit, but it's almost same. For Landsat is 16 to 17 days. They have fixed radiometric resolution, because when the sensor was built, they said that we are going to detect only the 8-bit of information. So Landsat up to Landsat 7, they have 8-bit information. And then when you come to excuse me, Landsat 8, they have now 12-bit information. Okay, so it's predefined, pre-built. We do not change them. However, when we talk about one sensor to another sensor, then our resolution started changing. For example, if we compare Aster and Landsat 7, Aster has 14 bands, whereas Landsat 7 has 6 bands, okay, or 7 bands, including the thermal band, right? So 7 bands. So one quick example, if you take one image from airborne data, so how would it look like? And it would look like this. And what do you see from this image? Okay, we see some land parcels. Okay, we see some bare lands, vegetations. The vegetations are going, and we're not really quite sure whether do we see sky, do we see the horizon here, because it's filled with some aerosols maybe, which are blocking the signals, or it's hazy, or they have some fogs, and there might be a river, but the outline of this river is not really identified. Okay, it's not clearly defined. And also, if we at our first glance, we do not realize that there is a river. Okay, then if we look into this near infrared data, you see, if we look into this near infrared data, so near infrared has, the water bodies has less reflectance, whereas vegetation and others has high reflectance in near infrared band. So since water has low reflectance or no reflectance, and rest of the objects or things from this image has high reflectance, of course, if you can imagine in a graph, the high and low, they have high differences. So we can easily identify the outline or the boundary or the extent of the river. So this river is known as Dragon Lake or Dragon River. I forgot the exact name. I think it's either Portugal or Spain. Have a quick look, Google, and you will find it. So it looks like dragon. You see this is the dragon, and it has these multiple legs. So from this image, it's not possible to identify the rivers are going like this. There is still rivers, okay? But then if we take only one band, and you can easily find out the information on the extent of river. So that's the beauty of remote sensing, okay? You can sometimes you can explore the things, sometimes you can see what naked human eye cannot see. Okay, so that's one quick example, and that's how the river looks like in reality. Okay, so this one is taken in a very clear, sunny day from another point of view. So radiometric resolution is, simply put, is the sensitivity of the sensor. So how sensitive the sensor is. If the sensor is very less sensitive, then it cannot identify the differences between the signals. However, if the sensor is very sensitive, then it could identify the difference between the signals. For example, if you have one sensitive tooth, for example, you have ache in your tooth, that means তোমার দাঁত ব্যথা করছে. You have a cavity in your tooth, তোমার দাঁত যে ফুটো হয়ে গিয়েছে. So now, if you are having one ice cream, then you are having this sensation, unpleasant sensation in your tooth, okay, or in your gum. So that's called sensitive. Whereas maybe your friend is having the same ice cream in the same temperature, but he or she is not feeling anything because they are less sensitive towards this coldness, right? So they are having this 1-bit information, and that one bit information cannot identify the temperature fluctuations, okay, because they are not sensitive. They can detect less differences of the changes of the temperature. For example, their tooth are protected, they are less sensitive. All right, so their radiometric resolution is very less. On the other hand, your tooth has 8-bit sensitivity. So your tooth can identify if it's that cold, if it is cold to the -10 degrees Celsius or -5 degrees Celsius. So it can start aching from -8 degrees Celsius. So if the ice cream is it can detect sensing from -5 degrees Celsius. So if the ice cream is warmer than -5 degrees Celsius, you can eat it without any problem. But as soon as it reaches -5 degrees Celsius, you start having problem. You start getting this toothache. And then if you decrease the temperature more, okay, if you go below this -5 degrees Celsius, the moment you started going below, then the pain started increasing with the decrease of the temperature. Okay, so that's sensitivity. That is radiometric resolution, how sensitive your image is. Okay, so one quick example is that, so 1 bit is 2 to the power 1. So what is 2 to the power 1?
So 2.
2, right? So it can detect only 2 sorts of information. Okay, this image can detect only 2 sorts of information. And this is 8-bit image. So 8-bit is 2 to the power 8 is 256, right? So it can detect 256 different signals. That's why you will find in this image there is white, gray, dark. Okay, but in this image there are lots of many other shades. In this image you will realize that this one is same color. Okay, because this image cannot identify the signal differences between this region. So that's why this image made this region as plain. Okay, one quick good example is the river or the water body. So the water is simply plain because these data cannot identify the differences of the signal. On the other hand, we have multiple shades on the right hand image because now this is more sensitive and it can identify a little bit of change in signal, and that's why it can identify where are the sediments higher, lower, or if there is any changes on the water body reflectance from the water bodies. So quick examples of the same location. 2-bit has 4 values. So we have 4 values, 4 different shades in this region, okay, containing less information. And then 4-bit 16 values. You see, you will look into this vegetation, this part, then you will realize it even more. So in this region, vegetation is, or the hills are plain. It does not have any changes between them, nor any shades. And also this region, okay, it does not have any shades. And this region, they're just plain. But then when we increase the bit, when we make it 16 values, it improves dramatically. Okay, now this one has multiple shades. Okay, and this one also has multiple shades. And the hills or these vegetations, now you can identify the bare land or the grassland from the trees. Okay, now it has multiple shades. And then when you increase the bit to 8-bit, which is 256 values, now it can even more identifiable. The objects are even more identifiable in this image, in this image, right? So all these things are having now more and more shades. So this a little bit of change in the signal can be detected by or can be recorded by the sensor. If you increase the bit a little more, if you make it 12-bit, for example, Landsat 8, it can now detect even more fluctuation in the signal. So that's one of the problems that I had in my master's thesis. So my master's thesis was on Chittagong hill tracts. I was trying to quantify the fluctuation of the carbon using satellite image. So how much carbon is being released? Simply carbon. I was trying to find out the carbon sequestration, whether it's positive or negative. So while doing so, I was using Landsat 4, 5, 7, and 8 images. And when I was trying to understand the vegetation, my Landsat 8 was giving me weird values. Okay, which does not go with the values of Landsat 4, 5, and 7. I didn't use 7, sorry, I used 4, 5, and 8. So finally, I realized that because of the change in radiometric resolution, since 4 and 5 has radiometric resolution of 8, and Landsat 8 has radiometric resolution of 12, so 12 is significantly higher. Okay, so 2 to the power 12 just tell me, I think it's more than 1000. So for 1 pixel, it can, if the 8-bit information was giving me a shade of green, for example, or a shade of red, 12-bit was giving me totally a different shade of red because it has 12-bit of information. So when I was comparing this data from these 3 different sensors, and then of course the Landsat 8 was giving me a reflectance value which is different than the other 2. Okay, so I was still learning at the time, so I didn't realize that it was the problem due to the radiometric resolution. So suddenly I realized that it's a problem with the radiometric resolution because it's 12. So I scaled it down to the 8 and the problem was solved. Okay, so you have to think of these things when you are working with this data. So the satellite collects data. I think we have already discussed all these things, however, very quickly. So the solar incidence falls onto the surface. The surface of Earth receives these visible lights. Some of the lights, the energy that falls onto the atmosphere, they get reflected by the atmosphere. So two types of protective barrier is functioning in our Earth. So one is the atmosphere. Okay, so the atmosphere is working as a barrier of the signals, and another one is the magnetic field created by the core of the Earth. Okay, so so it has a magnetic field going from North Pole to South Pole, and it protects us from the solar flares. Okay, so all the thermal energy is getting reflected, diverted into the space by these magnetic fields, whereas the UV, much powerful signals, the UV are getting reflected by the ozone layer and so other things. However, the visible lights, okay, which is short wave, we can call them short wave. So they comes in, they gets absorbed. Some of them gets absorbed by the atmosphere, and then some of the energy gets absorbed by the surface, and some of them or rest of them gets reflected. And also after the absorption of this energy, a little bit of energy is getting emitted from the surface of Earth. Also at the same time, the clouds, they also reflect some of the energy. So that's the reflected shortwave energy. So if you look into the width of the signals, you see how much energy is coming in and how much energy is getting lost to the clouds, and then how much energy is getting again absorbed by the surface. Only a little percentage or little portion of the energy is getting reflected by the surface of Earth, and a significant is getting reflected by the clouds. So ultimately, what we are receiving at the sensor's end is even maybe 1/3 of the energy that is coming in, or sometimes even less than this 1/3. Okay, so very little amount of energy that sensors are absorbing. Anyway, so that's the end of today's class. Any question? Does anyone have any question? Okay, so no question. Okay, stop sharing, stop recording, and thank you.